Officially, I welcome you all to the Viva examination of my candidate, Mr. Cheriyan Ebenezer. I have two duties now. One to introduce the candidate. Cheriyan Ebenezer did his BSc from Udhampur, Jammu and Kashmir, and then MSc in Madras Christian College. And I joined here in 2016, and he was my first batch of student. So at that time, I asked, like, do you want to do PhD? He said no. Then God brought him here, and then he got a lot of important things in his career. He has got a special prize in second MSc, and then 2017 and 2018, and he joined as a project assistant in my project DST SCRB project under Early Career Research Award, and then subsequently he has promoted as a JRF, and then he has got a lot of awards from the college for his research publications. And more importantly, he has published 32 research publications during the stay here in MCC. I think that is an MCC record. So it did well, and then the task that I gave him is like, you should publish at least 10 first author paper. And he's like a good government servant. He exactly published 10 first author paper. And then he said, no, that's fine. No, I didn't expect that. Then I asked him to write a review, and then he eventually wrote a review, and it got published. And I can proudly say that he's a candidate whose thesis contains a lot of letters, and all letters are published except the certificate page. That is a great thing, because the introduction is published as a review article, and then the rest of the 5 chapters, I asked him to take any 5 chapters, because he published 10 papers, and then he picked 5 papers of his choice, and eventually we have adopted that as a thesis. And so I'm very proud and privileged to have him as my first PhD student. And now, so is the case that the external examiner is also having a lot of laurels in his credit. And if I really want to go through the CV, it will take another 10 minutes. So I just give it in a nutshell that he is a prolific academician, including teaching and research. And his studies is from Gujarat, writing from BSc, MSc, and PhD, and then he has got postdoc from different countries. There are a lot of awards. You just look at that, and a few I have mentioned, I can collect, but there are a lot of awards that he has got. Especially, he has got 4 patents, 3 Indian patent and 1 international patent, and around 270 plus publications with a citation count of nearly 10,000, and the H index of 51 and I-10 index of 166, which means that is really good. And when I gave the reviewers list, I picked Sir, and later I looked at the profile. He's so good in doing that separation studies, especially in liquid junction and so on. And he has also have some computational papers too, and therefore is the right candidate and the best bet for being a adjudicator at this external Viva examination. Without further delay, I would like to hand over the session to our external examiner, Dr. Ramesh Prabhas. Over to you, sir. Yeah. So I request Cheriyan Ebenezer to briefly present his findings of his thesis for about 25 to 30 minutes, followed by we'll have questions from the audience as well as the examiners. Over to Cheriyan.
So, good morning everybody. So my thesis title is DFT Studies for the Systematic Development of Molecular Frameworks for Preferential Binding of Americium Ions over Europium Ions in Nuclear Waste Management Treatment. Okay, so basically I have 6 chapters. I start with Introduction and Methodology. Then I study the impact of coordination modes of N-donor ligands on americium and Europium separation. Then further I go ahead and substitute phenolic groups at 5th and 6th positions with change in aliphatic ring size for selectively separating americium and Europium. In the fourth chapter deals with the influence of alkyl chain, how alkyl chain influences the selectivity, and 5th chapter is based on the pre-organization of NO hybrid 110 phenanthrolene derived phosphine oxide ligand with different cyclic substitution. And finally, I end with the sixth chapter and summary. Okay. Okay, so the first chapter is Introduction to Ligand Design and Computational Methodology. So, as we all know that fossil fuels are a source of great carbon emissions. Apart from this, non-fossil fuels also generate a lot of carbon emissions. To tackle this, nowadays we are using nuclear energy. It has both advantages as well as disadvantages. Some of the advantages are low carbon energy, reduced greenhouse gas emissions, high energy output, stable and continuous energy supply, and long fuel life. But with every advantage, there are some disadvantages also. Disposal of these waste is one of the main problems that we face. And initially, we have high cost to set up the nuclear power plant. Going on further, in the nuclear fuel cycle, first we have the mining and milling process. So the uranium ore is first extracted, then it is converted and enriched. So first the process is mining. We'll extract uranium, and then we'll convert it, and then we enrich it with gases. Okay. Then we have the fuel fabrication state, and then it goes to the nuclear reactor, where different uranium fusion takes place, and products are formed which are unstable. So then we have the spent nuclear fuel. So in the spent nuclear fuel, if uranium is remaining behind and plutonium is remaining behind, we'll use it again. But along with it, some minor actinides are there. Some minor actinides like americium are there, and lanthanides are also there. So my job is to separate americium from europium. So I have basically taken them because if we don't separate them, then it will lead to greater toxicity. So the basic principle that we use here is the HSAB principle. So we know that hard acid prefers hard base, and soft acid prefers soft base. So we'll take hard acid and hard base, or if it is the soft acid, we'll take soft base. So americium and europium are hard ions, but americium ions are slightly softer than europium ions. So therefore we'll use soft end donor ligands. So that's why I'm using soft end donor ligands, because americium is slightly softer than europium. So these are some of the ligands that have end donor atoms in them, and such ligands are preferred for extraction of americium over europium. So now coming to the computational part. So basically I have done full computational. I have not done any experimental work. So first of all, we have calculated bond order. We have checked the bond lengths. We have done thermodynamic analysis, population analysis, quantum theory of atoms in molecules, and energy decomposition analysis. So this paper I published as a review article. It was published in Commons on Inorganic Chemistry. So here I end with the first chapter. In the second chapter, the title of my second chapter is Impact of Coordination Modes of End Donor Ligands on Americium and Europium Separation. This also was published in Chemistry Select. So the main motivation is that, see, many ligands are there which will be optimum for selectivity and complexation. So I have taken coordinating modes 2, 3, 4 and 5 and checked out which is better. So these are the optimized geometry. I optimized them in ADF software. And this is the potential energy surface diagram. From this we can see that there is CC bond rotation. So we have to find out which is the most stable state. And I found out that at 180-degree dihedral angle, it is the most stable state for TPDCM. Then I did natural population analysis. From this analysis, it was observed that the nitrogen atoms have lower negative charge than oxygen atoms, and negative charge surge on nitrogen and oxygen was observed upon complexation. And Bt-Fen complexes exhibit greater del QL values. Charge on the metal atom decreased significantly. So apart from that, while optimizing, after optimizing, I checked the bond order of all the Mn and Mo bonds, and it was observed that the bond order of americium with the ligands, the nitrogen atoms and the oxygen atoms were greater. So that means they are complexing better. And then I did QTEM analysis also. From the QTM analysis, it is almost the same thing. I'll find out the electron density. So greater the electron density, greater is the binding. So I observed that greater electron density was observed in americium complexes over EU complexes. Then I checked the del G values for americium and europium and found out the del G, that is the change in Gibbs free energy between the americium and europium complexes. And from there I calculated the separation factors, and it was found out that the separation factor for BTP ligand was the greatest. I also did energy decomposition analysis. So basically in energy decomposition analysis, we segregate the bonding energy into orbital, electrostatic and Pauli's repulsion. And it was observed that in europium complexes, electrostatic interactions were more, whereas in americium complexes orbital interactions were more. And I did the molecular orbital analysis also. From that we can find the HOMO-LUMO gap and check whether it's stable or not. So conclusions of the first chapter: americium AMN and AMO bonds are stronger than EUN and EUO bonds. A significant increase in the charges of N and O atoms occurs upon complexation. BTP ligand exhibits strong Mn bonds, and the most selective among all the ligands, the 4 ligands that I chose, BTP had BTP was the most selective one. As number of coordinating atoms increases, the binding energy increases. So if we increase the number of coordinating atoms, the binding energy increases. But that doesn't hold for selectivity. Selectivity depends on the strength of Mn, MnO bonds. And as I mentioned earlier, orbital interactions are mainly responsible for the formation of americium complexes, while electrostatic interactions play a key role in the formation of EU complexes. To improve the binding efficiency of organic ligands, one can go for higher coordination modes. So binding efficiency, if we want to increase, we can go for higher coordination modes. While to achieve selectivity enhancement, one can think of tuning the strength of coordinating bonds. So this is a paper that got published in Chemistry Select. Coming to the second chapter, tailoring the selectivity of phenanthrolene derivatives for the partitioning of trivalent americium and europium ions. So the motivation for this work is that I wanted to do modification on the phenanthrolene backbone of CYME4-BT-Fen. So we know that electron donating groups such as phenol influence the extraction capability, and it was found out from literature that 5th and 6th position were the most suitable one. And also tuning the aliphatic ring also altered the cavity size of the ligand. And so I did substitutions on 5th and 6th positions of the BT-fen, CYME4 BT-fen, and I also changed the aliphatic ring size. So these are the optimized geometry as observed earlier. Americium had stronger bonds compared to europium. And the frontier molecular orbital diagram is given here. And next, the natural population analysis as observed earlier. Charges were calculated. The charges on N1 and N4 are greatest in americium, implying ligand 3 complexes best with americium. Charges on N1 and N4 are lower in americium complexes than in EU complexes. The charges on N nitrogen indicates upon complexation the metal firmly fits into the cavity of the ligands. Then similarly I did quantum theory of atoms in molecules, and the electron density was greater in case of americium than in europium. And similarly, like earlier, here also I calculated the energy decomposition analysis, and the total binding energy was calculated. From the thermodynamic properties, it was found out that ligand 5 has the best separation factor. So coming to the conclusions, CYME4 BT-fen derivatives show better binding behavior with trivalent americium than with trivalent europium ions. MN1 and MN4 bonds are stronger compared to MN2 and MN3 bonds. 6-membered CME4 BT-fen derivatives with phenol substitutions at 5th and 6th positions, that is the third ligand, are found to have greater complexation ability to extract americium ions compared to other ligands. Extra stabilization was observed through QTM analysis. N.O and N.N interactions were observed with NO3 molecules. And like observed earlier in the earlier chapter, orbital energy contributed greatly to the binding in americium complexes, whereas electrostatic interactions contributed greatly to the europium ions. So this was published in ICF, Inorganic Chemistry Frontiers. So coming to the fourth chapter, the fourth chapter's title is Does the length of the alkyl chain affect the complexation and selectivity of phenanthrolene derived phosphine ligands? So the motivation of of this chapter is that people did work on diethyl and dibutyl. So they never checked, should we increase the length, what is the optimum length, alkyl length. So I tried to find out that in this chapter. So these are the optimized geometry. First ligand will have methyl, second ethyl, propyl, butyl, similarly, and similar things were observed. So americium complexes had greater bond order compared to EU complexes. So Mulliken charges, again the same thing was observed in this case also. Metal charges decrease significantly from +3. Greater negative charge is observed on oxygen atoms than in nitrogen atoms. Negative charge on nitrogen and oxygen atoms increases when the ligands form complexes. Oxygen atoms on the ligands play a crucial role in complexation. So here also I calculated the quantum theory of atoms in molecules, and I found the electron density, and the electron density in americium complexes was greater than in europium complexes. Like all other chapters, here also I did the energy decomposition analysis, and we found out that electrostatic interaction is predominant over the repulsion, and in americium complexes the total binding energy is primarily arising from the orbital interactions. So here also I did the thermodynamic analysis, and it was observed that the ligand 4 had the greatest separation factor. So concluding this chapter, CH.O weak interactions stabilize the ligands and their complexes in addition to the coordination bonds. Oxygen atoms in the ligands play a great role in complexation process than nitrogen atoms. Americium complexes have greater MNO bond order than EU complexes. Complex formation reactions are exothermic and spontaneous. Ligands tend to bind strongly to americium ions over EU ions, and butyl substitution exhibit better selectivity and higher binding ability towards americium ion. So this chapter was published in Polyhedron. Coming to chapter number 5, uptake of americium ion and EU ions using cyclic substituted NO hybrid 110 phenanthrolene derived phosphine oxide ligands. So the motivation of this work is, so basically we had a phenyl group attached to BP phen, but other cyclic substitutions were not done. So I plan to do other cyclic substitutions and find out whether it increases the efficiency of extraction. So again, here we have the optimized geometries of all the complexes, and the bond orders similarly were calculated, and it was found out that americium complexes had greater bond order than European complexes. And in molecular population analysis, again the charges were calculated, and again these diagrams are from the quantum theory of atoms in molecule, and the electron density was calculated. And then energy decomposition analysis was observed, and it was observed that orbital interactions are found to be higher than the electrostatic interaction in americium complexes, while the opposite is observed in EU complexes. Coming to the thermodynamic part, the substitution with cyclic 6 group was better than the other substitutions. So concluding this chapter, it was observed that molecular charge analysis, bond order analysis, QTM analysis and ED analysis watch for greater binding of CY5. AR5 showed better selectivity in uptaking americium ion over europium ion through higher del G values. AM analysis also discloses that there are many CH.O weak interactions which stabilize these complexes in addition to the MON bonds. EDA reveals that in americium complexes the orbital interactions play a key role in total binding energy, while in EU complexes electrostatic interactions play a significant role towards total binding energy. And this was published in Chemistry Select. Coming to the last chapter, pre-organization of NO hybrid phosphine oxide chelators for effective extraction of trivalent americium over europium ions. So the motivation again, here we have phosphorus in it. So again, nobody has done a cyclic substitution and checked out whether it's good or not. And here I took it a little bit further. You might have observed I did 1:1 complexation. In this case, in this chapter, I have done 1:2 also. So these are the optimized geometry of 1:1 complexes, and the bond order, as observed earlier, americium complexes had better bond orders than europium complexes, and similarly molecular population analysis was calculated. Again QTM was done, and the electron density was calculated. Here so one more thing that we did in this final chapter is that we included solvation. So we use solvation models to mimic solvation, and thermodynamic properties were calculated, and the second ligand had the greatest del G value. And as mentioned earlier, I did the calculations for 1:2 complexes also. So here we have 2 ligands along with 1 metal atom. And from the coming to the conclusion, ligands with pyrrole substitution exhibited greater abstraction capability towards americium ions over europium ions. Completion ability is greater in ligands having phenyl substitution, both in the case of 1:1 complexes and 1:2 complexes. EDO proposes that all the ligands inclined to bind intensely to americium ions over europium ions, irrespective of complexation, phenanthroline phenyl combination. So phenanthroline phenyl combination exhibited better extraction abilities. EDS suggests that in americium complexes, the total binding energy is due to orbital interaction. So this was published in New Journal of Chemistry. Coming to the summary of my thesis, so computational ligand design, from that we can understand that it saves time and resources by identifying promising ligands which can be further taken up by experimentalists, so that it will save time for them, and it enables tailoring ligand properties to meet specific separation needs. From coordination and binding ability, we understand that it challenges the assumption that more coordinating atoms result in higher binding ability, and it emphasizes the need to consider multiple factors for selective separation of actinides and lanthanides ion. Selective separation, if you look into the selective separation of americium over europium, we found out that phenanthroline based ligands with symmetrical phenol substitution enhance the americium selectivity. And if we look into the alkyl and cyclic substitution, so what kind of substitution is required, I would suggest that alkyl substitution and butyl groups improve separation efficiency, whereas in cyclic substitution 5-membered aromatic rings optimize binding. Thank you.
Good work, good presentation, Cheriyan. And
Thank
you
you.
took 24 minutes, so I have a right to take 24 minutes. You can take water anytime in between.
Sure.
You can take your thesis anytime between, and you can free to write on the board anytime whenever you want. Okay, and you can go through slides anytime. So
Sure.
these are allowed.
Okay.
So let me first congratulate you
Thank
for
you,
a
sir.
nice work and so many good papers.
Thank you, sir.
Now let me be very critical. You need not to afraid. Okay, you have to defend. Okay. Let me start with the biggest negative. Okay, don't afraid. You have to defend.
Yes, sir.
All your work is useless because you have done only in the computer.
Yes.
You have never compared with the real experiment, real scenario. How you defend?
So actually, sir, all these works are derived from experimental works only.
Why you have not compared anywhere? Why you have not shown any comparison with any results? Is it there in the thesis?
Yes, sir.
Okay, can you just elaborate little bit? Which group you experiments you followed and what was the experiment? Let us, these questions you can answer in between any time. Okay, let us start. This is the biggest question. You keep defending this. Okay, let us start with your nuclear fuel cycle, slide 8. Go to the slide mode and put 8. Okay, slide 8. Yeah. So now the first question, why you need to separate americium from europium? First question, and where we are talking, which place we are talking in the real nuclear fuel cycle.
Okay, sir. So basically, once the fuel has been used, there will be spent.
See, if you be short and crisp and to the point, we will finish early. Otherwise, my taxi driver will wait. I am not going to leave. Please be short, crisp, and to the point. You don't know answer also, no problem. Where we are talking, which place we are talking, Americium we need to be preferentially separated compared to Europeum.
Before the final deposition, sir.
So final deposition.
Before that.
Before final deposition, it's around spent fuel.
Yes, sir. Yes, sir. Yes, sir.
This is nice, no? Don't tell all this. That's okay. Now, what could be the phase? Phase, PHASE, phase.
Okay.
What could be the phase? I'll give you three options. There may be many, okay? Solid, liquid, mixture, solution, gas, or vapor, or supercritical. What is the phase?
It's a liquid phase, sir.
Okay, liquid phase. Okay. Now come to your computational work. Any chapter. What is the basis set? Can you just take a pen and write basis set? Is it okay? Huh?
Yes, sir.
Or you tell. Either is fine for me. Which basis set? They will help you. Okay, they will get pen. Meanwhile, you tell. Basis set.
Sir, BP86, sir.
Now, what is the phase we are talking? What is the phase?
Liquid.
B3L1. How you consider the liquid surrounding? What is the model? Is it a polarity model or how you consider the liquid-liquid interactions?
So basically due to computational constraint, we have done it in gaseous phase only.
Yes, that's what I'm
Gaseous
asking.
phase. So we have done it in gaseous phase. Only for the last chapter, we have used a solvation model.
Yes, the last chapter you used the solvation model 60. Just type 60 and enter. 60 and enter. Oh, this 60. Solvation model where you showed 60 only, no? Before.
Yes, sir. Last.
Yeah, this one only you showed. Here only you showed. So what is the difference earlier chapters and here?
So in earlier chapters, everything was calculated in gas phase. In this, we tried to mimic the solvent model. We used a solvent model to mimic the solvation factor.
Use the scientific term. Did you use dipole moment or did you use polarity? What do you mean solvation model?
So there basically two models are there in computational aspect: explicit and implicit.
Yes. What it mean?
So implicit is that we just take the dielectric constants and we mimic it. And explicit is we just manually put a number of water molecules. So explicit we didn't do.
Okay.
We did implicit.
Okay. So no problem. So now my 0th question. Okay. What was that? Your real extraction is in solution phase or the bulk phase. All your chapters are gas phase.
Yes, sir.
How you will defend? And you told, you compared with literature, experiments and matching. How it is matching? You should not match, no?
Yes, so basically the ligand that I took as the base ligand, that I compared. The modifications I can't compare.
You can't compare.
Yes, sir. Yes,
Have
sir.
you compared with other computational models or other people's work?
Yes, sir. Yes, sir. No, I compared with the experimental work, sir. Experimental work.
Others computational thing
No.
or other things?
No.
Or, okay.
No.
These are the new ligands, that's why?
Yes, sir. Yes, sir.
Okay. We'll come to our first page, there only you go. 8 on nuclear fuel cycle. 8. Enter. So, you said that both are hard, Americium and Europeum,
Yes,
but
sir.
compared to Europeum, Americium is slightly
It's softer.
What made you to make this statement? On what basis? Is it bond ability, bond order, polarity, bond distance, or separating through, or this both of them trivalent, no?
Yes, sir.
What is the counter anion you are thinking anytime, if at all you are thinking? Is it chloride?
Yes, sir. NO3.
Or nitrate?
Nitrite. So I have used NO3. So
NO3.
three NO3s are always.
Why NO3? Do you know why NO3? NO3 is right. Okay. Why
Yeah.
NO3? Have you heard HLLW?
High level liquid waste.
That's what you are trying to. From where you want to separate Americium and Europeum?
High level
liquid waste.
waste.
And that is a
Nitric acid medium.
Nitric acid medium. What is the pH, you know? No, no, I'm telling in reality. In reality, just nearby our IG car,
Yes, sir.
Kalpana.
Yes, sir.
You
Yes,
could
sir.
have gone and discussed with somebody
Yes,
the
sir.
reality.
Yes,
And but how you make your medium acidic? Tell me. In your gaseous phase,
Yes,
what
sir.
you consider? Only ligand you consider? Only metal trivalent you consider?
No, sir. Metal is combined with 3 NO3 molecules.
3NO3 you have
Yes, sir.
considered.
Yes, sir. I have
3NO3.
considered in all gases, gaseous as well as in liquid. Solvation also I have considered.
Can you just next slide little bit ligands now? What is the choice? Why you choose this kind of ligand? Of course, I understand you want a triazolium based and all these things.
Yes, sir.
But even in this, how many are here? 5, 4, 9 plus 13. 13. Okay.
Yes, sir.
Why you choose this 13 only?
So basically, my work is totally based on nitrogen-based donor ligands. So those type of ligands I have shown here, and nitrogen being slightly soft, I have taken those.
See, in entire this 13, where the number of CN bonds are more compared to CH? Is it this one, BP? More CN or NN bonds compared to CH? Is that matter? In your separation, will that matter? Number of CH bonds or number of CN or NN bonds are higher compared to CH bonds?
So number of donor atoms greater if the number of donor atoms.
Where highest? 3. 3. Where are they?
So we have.
See, in the first chapter you told TPDCl is better. Where is the TPDCl? This is from the literature, not the you one
sir.
use.
No,
okay,
sir,
not
no.
the you.
No.
This is from the literature.
Yes, sir. Yes, sir.
So we'll go to where you have used the ligands. Maybe next chapter, next slide 10. Yes, computational method here only. So can you just elaborate here on the basis set and why you choose only 1:1 complex and how you think that as much as possible you are mimicking the real scenario?
Okay.
What are the precautions you have taken while choice of basis set and other things and input parameter? You have to give, no?
Yes, sir.
Computer will not give just like that.
Yes, sir.
What are the input parameters and how you taken care of?
So, sir, I used BP86 and TZP, and I did benchmarking with the experimental paper. So, if I correlate with the computational paper, that would not give a correct idea.
How many experimental works? 1, 2, 3,
Sir,
many?
all of them.
All of them, whatever available.
All of the no, sir. All of the works I have compared with the corresponding experimental papers.
How many corresponding? One or many?
So each chapter has a corresponding one experimental
One
paper.
experiment. If that experiment is wrong,
True, sir.
may have experimental error, no?
Yes, sir.
See,
Yes,
like you have computational error.
Yes, sir.
They have experimental,
Experimental error.
Anyway, I understand this. That's how the science grows. Now, elaborate little bit.
Okay, so I have done all of these analysis, and these analysis will help us understand the binding and selectivity. So bond order, population analysis, QTM analysis, these all will tell about the bonding, how it is binding to the metal ion. At the same time, thermodynamic and energy decomposition analysis will give the selectivity.
So you can take your thesis, okay? Pen is not there. Pen marker. Are you comfortable to draw any one ligand and any either americium or UF metal, and you explain where is the bond you are telling, what is the mechanism, how it prefer americium compared to any chapter, any ligand? Are you okay? And you can see your thesis. You explain us how you mention so many things. Then binding constant higher, Mn bond is MO bond, so many things. You want slide 22 will help you. Slide 22 you go. 22, 2 and enter, 2 and enter. Yeah, here you said so many things. More ligand is better, Mn bond is better, this is thermodynamics better. You can just draw and explain little bit, like you are explaining to MSc student. Any ligand you draw, whatever you like. Which chapter you are taking? Okay. No problem, no problem. Go ahead, go ahead. Do a little bit fast, no need to be exactly accurate. Benzene ring, no need to be all bond angles same. Assume all of us are now MSc students, including your guide. What is the page number?
Page number 59, sir.
Okay. You are drawing BT pen, huh? PHEN. Okay. So for this you have now only one americium and 3 NO3 groups. Huh? So why it will prefer americium over europium? Just you explain. What is the mechanism? Which bond order from where to where?
Americium nitrogen, americium nitrogen, americium nitrogen, americium nitrogen.
4 bonds or 4 average of 4?
No, sir.
4 separate
Four
bonds.
separate bonds.
Okay, okay.
Similarly, europium also we calculated.
Huh.
We found out that americium and bonds are far superior.
Means
They have higher bond order. They have higher bond order than europium.
higher bond order means more distance or less distance?
Less distance.
So stronger, binding stronger.
Yeah, binding stronger.
Yeah.
Binding stronger. And at the same time, QTM analysis for each bond, we calculate the electron density there. And from the electron, higher the electron density, greater, stronger bonds would be there.
How about delta G? You talk here delta G. This is chapter 3, huh? Chapter 3 or chapter 2? Chapter 3. Chapter 3 means you are talking about MN1 bond and MN4 bonds are stronger compared to MN2 and MN3. Which is M1, M2, M3, N1, N2, N3, N4? You spoke, no, this one? Yeah, somebody can put 32, slide 32. Or I can, why how all pages are here. 32, 3 to enter. 3 to enter. It's not going, huh? 3 to enter. Ah, okay. This is the one you spoke, no?
Yes, sir.
You are talking same molecule, no?
Yes, sir.
Yeah, can you show what is M1, N1, N2, N3, N4?
N2, N3, N4.
Now you tell me why N1 and N4 are stronger compared to N2 and N3.
N1 and N3.
That's the second statement.
Yeah. So the bond order and the bond length observed in these two was the bond order was greater than this two.
Cheriyan, I agree with you. Whatever you observed, you are telling. I am telling why you observed so. The question is, I am not doubting your results.
Okay.
I am asking why so. Can you go more deeper? Throughout your presentation is good for the results obtained. You never try to go into deeper why it is happening like that only. You got my point?
Yes, sir.
Okay. Look into that, huh? Let us come back here. 17. It's okay. You clean later on. Or we'll take photo there last. 17 bond order. This is one you are talking, no? Bond
Yes, sir.
order for
Yes,
this
sir.
one. Yeah.
Yes, sir.
Yeah. See, when you say 0.100, 0.101, okay, I am talking of EU, BT, PHEN
Yes.
for MN2 and MN3.
Yes, sir.
Okay, how we can say which is large? What could be the accuracy? What could be the significant digit? Or what could be the error? Everything has error, no?
Yes, sir.
Huh?
True.
Experiments also have error,
Error.
computation also have error.
Yes, sir.
Is your error is fourth decimal or third decimal?
So third decimal, sir.
Why? Why not second decimal? How to calculate? Let's say you want to calculate error. In experiments, I know how to calculate error.
Yes, sir.
One way is 3 times you repeat and then take. Other way is error associated with each parameter I know and I will do error propagation. How you will do it? See, your error will come from where? Only input parameters.
Yes, sir.
What are the input parameters?
The basis set.
That you cannot do anything.
If I can't do anything, then the
Ligand to metal you put 1 1 only.
Yes.
Metal is trivalent, NO3. Where the error will come? What else your input parameters? Nothing?
basis set, functional, then a zero order relativistic approximation. So error might come from there.
Structure?
Yeah, structure, input structure also, error might come from there.
18 next. You said electron density is more, binding is more.
Yes, sir.
Can you elaborate little bit? Electron density is more, binding is more.
So basically in QTM analysis we find the electron density that is between two atoms. So I have found out the electron density between the nitrogen and americium atom, at the same time nitrogen and europium atom. So electron density is greater in americium complexes. Bond critical point.
Next, what is the unit for delta G? You never put units anywhere. Is it electron volt or kilocalorie per mole? I gave you only two options.
Kilocalorie per mole.
How people will know? And here again accuracy. 0.01 you have accuracy.
Yes, sir.
See, computation will give you any digit you want.
Yes, sir. Yes, sir.
It can give 4 decimal also, 10 decimal also.
True, sir.
Huh?
True, sir.
You should know what is the significant digit. In reality, is it possible experimentally 0.01 delta G values? 0.01 kilocalorie per mole, is it possible? Very difficult. Very, very difficult. It's possible, but
Yes,
it's very
sir.
difficult. What do you mean by minus here? We all know that delta G minus means spontaneous, and so it's both are spontaneous.
Yes, sir. Both are spontaneous.
Then,
Sir.
see, in the first one you see,
Yes,
307.91, 307.88. Almost
Same,
close.
almost
Almost
close,
same.
yes,
Last
sir.
also. Last also.
Yes, sir.
No. This is last is below. But first one only very close.
Yes, sir. Very close.
And you are still telling that that only it will be measured. Americium will be preferred.
Sir, it will be slightly. Sir, that's not that great, sir.
Yeah.
So if you see the separation
So
factor.
that's why you told TPDCA is better.
Yes, sir.
Yeah. And
So BTP is better, sir. BTP is.
Here, how about time? Are we silent about time? You are preferring americium. It's a spontaneous.
Yes, sir.
Are we silent about time? Will it take seconds or days or years?
Sir, that molecular simulations should be done, then only we'll know. So that is future work.
Yeah, you never talked about time, no? Anyway, when thermodynamics we talk, we don't talk about time. Only in kinetics we talk. 22, you said BTP, this one is most selective. Here the values are not matching. You see here BTP, go back, 18 or 19, next one, whatever this. Are you telling BTP is better?
Yes, sir.
Or because of 5, minus 5, okay.
Yes, sir.
22 you go. So, how many ways you are telling which ligand is better? See, you wrote so many things. Mn bond, then this delta G, then all of them are contributing. Can you tell me what are the things contributing for selective separation?
So for americium, it's the orbital interaction.
One is orbital interaction.
Orbital interaction. So
Two, that Mn bonds also you are talking.
yes, yes.
Three,
It's charges.
charges.
Charge.
4, electron density also you are talking.
Yes, sir.
Then 5, you told one more thing also.
Selectivity,
Separation factor. And delta G also you told. All this together. So which is most crucial? Because is there any way?
so separation factor is the most crucial according to me, because we need to separate. Complexation is secondary.
Separation happens due to complex only.
Yeah, true. But our aim is to selectively separate. Even if complexation is less.
What do you call that is F or partition coefficient? What do you call that separation factor?
SF, sir. SF factor.
Anywhere you show me that?
Yes, sir. In the thermodynamic. SF. Last one. Yeah.
Okay. This is separating from where to where? Can you just tell me from where to where we are separating?
So americium over europium.
I understand.
So from the delta.
Both are together. Both are together. Where they are together?
In the high level liquid waste.
HLLW. Okay, that I only told, but
Yes.
that's the one I
Yes,
know.
sir.
From there, where you want to take?
Where we want to take the.
See, when we say separate and again not in bulk phase.
Yes, sir. Yes,
you want
sir.
to take. So what is the other medium you choose in your in your computation? What, from which medium to which medium you are separating? Both liquid to liquid only separating?
So we did everything in gas phase, sir.
I understand. Gas to gas only?
Yes, sir.
See, separation means two things would be there, no?
Yes, sir.
You understood my question?
Yes, sir. One has to be taken out and kept in
Yes,
something
from
else.
where you are taking? From HLW you are taking. From where you taking? From
Nitric acid medium, sir.
that you should be clear, okay? That you should be clear. So you are separating. See, separating from bulk is one force you need or one energy you need. But where you are putting, there also it required more energy or not, we don't know.
Yes, sir.
Isn't it? So it is like a taking money from your pocket,
Pocket.
but whom you are giving, you are not mentioning.
Okay.
You have to be very careful with that. Usually in liquid, you take from one phase to other phase, both are liquid. Because of the polarity, they are different.
Okay.
And usually both are water rich. So the separation would be more easier. And we call partition coefficient
But yes, sir. In
Okay.
experiment.
in experiment. Anyway, I am just seeing my 24 minutes are over or not yet. Almost over. I just crossed 24 minutes. Can I take 1 or 2 minutes more?
Sure, sir.
Huh?
Sure, sir.
I crossed 24 minutes. 11:40 to 12. I'll take 3-4 minutes, man. Huh? You are lucky you finished fast. Otherwise, I could have taken more time. 36, you go alkyl chain length. I have so many questions. I will give this to you, okay? This is a gift from my side.
Thank you, sir.
Okay, you know, alkyl chain length, any property, you cannot compare with 1 and 2. Actually, the alkyl chain length effect start with 2 and you cannot go beyond 7. See, why you stopped butyl? Did you take pentyl and hexyl?
Yes.
Huh?
Yes. It didn't come out well. Sir.
Okay. Did you take octyl and above?
No. Up till octyl, sir.
It won't work. Even if you take, it won't work.
It
Why?
won't work.
Because the chain will bend. Bending.
Yes, sir. Yes.
So
sir.
you cannot compare 1. You cannot compare 8 above. When you want alkyl chain length, you can compare only 2 to 7 or 2 to 6 or 2 to 7.
Yes, sir.
But you are started comparing with 1. That's why all your plots are down and then going up.
Yes,
Go
sir.
next slide. Yeah, all plots are because you are comparing with 1. Because you cannot put any solid reason when you want to compare alkyl chain length. You have to start with 2 onwards. Okay. Anyway, this is one observation. And you told ligand 41 slide, ligand 4 has a greater separation factor. Why? 41, ligand 4.
So, It's minus 4.0.
I could see that. Why? Can you go to these ligands and show?
Four is N-butyl.
Because of alkyl chain,
Alkyl.
because of hydrophobicity.
Yeah.
You have to explain what is happening. So that means you are going from polar to little bit non-polar
Non-polar.
side. That's why hydrophobicity helping.
Yes, sir.
You should feel like a chemist, no? You should not feel like a mathematician. You should feel like chemists. Chapter 5 motivation. Anyway, it's 47 bond order. You suddenly increased one decimal. I think computer gave you more digits here. Huh? All places 3 decimal, or here you give 4 decimal.
Oh.
Isn't it?
Yeah.
When I could notice, anybody could notice.
Yes.
Okay. You see, we have to be extremely careful when we present this data. And the zeal, what was there, you thought it is exactly same, it is exactly. Lot of hard work. You presented such a way, it's only chapter 1 is important, remaining all are same. The enthusiasm and zeal, the way you present is not there. And you need not to put exactly this. Once you put a table, other time you put a figure. Once you put a figure, can any of your figure legends are visible? I am the first row. Still I am struggling to see. If you trouble me and give pain to my eye, I will give pain to you.
Yes, sir.
What about the last guy? None of your figure or most of your figures are not good. I am not telling the content, I am telling the visibility.
Visibility.
It has to be put some. See, thesis is different. Presentation is different. You do more work. And initially slide numbers was not there. I was struggling to put slide number. Later on slide number came. From 9 slide number came. 1 to 8 slide numbers were not there. And what are the overall objective? Other than thesis title, you can see the title. But other than thesis title, what is your overall objective? I know that you want to have a selective separation of americium over europium. But little bit, can you elaborate?
Okay, so basically we wanted to design new ligands and how the length and whether cyclic substitutions are needed or not. So that we tried to find out.
You wanted faster, or you want cheaper, or you want, what is your motive? Let's say when it goes to the real industry level, nuclear industry wants to take your data and do mimic there. Are you going to be sustainable, means environmental friendly, or a cheaper, means cost is down, or a faster? What is the motive?
So all of these ligands are environmentally friendly because it has a CHON concept associated with it. So none of them are harmful.
Yeah, so when I ask objective, you should start in the current, what are the problem, and with your answers, how we will solve it. Go to summary. Summary 65. Yeah, so whatever you told objective is a question.
Yes, sir.
And this is the answer. Okay. So now is it matching? Your objective, you didn't tell this much detail.
Yes.
Okay. Now you entire summary, can you tell in 2 lines?
So basically, if we want to do an alkyl chain substitution, N-butyl will be the best. And for cyclic substitution, 5-member aromatic ring along with phenanthrolene based ligands. That would be the best bet.
My second last question, or third last. You choose only in the last chapter metal to ligand 1:2.
Yes, sir.
And earlier chapter 1:1.
Yes, sir.
That's not a problem. What is the difference in choosing 1:1 and 1:2? What is a better, or what is your view? See, 2 ligand means it's expensive, that I can say.
Yes, sir.
But if it is separating more, that is a different. What is overall your view? What is in reality might be happen in experiment?
Sir, in reality, 1:2 is possible, more predominant.
Then your chapter 2, 3, 4 are not good.
Yes, sir, I know that.
Huh?
But sir, they might form 1:2 also. But due to computational constraints, we stick down to 1:1 complexes.
How much time it will take to understand one complex and one ligand? You give input and output is coming. In between, how much time you are waiting?
Sir, it took approximately
Not entire thesis, only one
no,
work.
1 week, sir.
Yeah.
1 week.
1 week. What you do in this 1 week? What you might be thinking? What is happening to my metal? What is happening to my ligand while drinking coffee? Have you ever thought? I don't care. Only you say power should not go.
Power will not go. We have
Because you
UPS.
have UPS. What might be happening? Why it takes 1 week? Tell me. Why it takes 1 week?
So because these are heavy metals, sir. Heavy metals will take lots of time, sir.
Why you tell little bit elaborative. Heavy metal takes time means what?
Optimization of the heavy metals
The
take time.
number of optimization you see, or number of bonds you see, the number of parameters you screen.
Electrons, electrons in americium and europium are greater than the small lightweight atoms.
See, it will say finally one answer is right. Before that, how many times it do iterate, and what is the speed at it will check, how many iteration you should see. You should explain to your grandmom or grandfather why you just submit and wait 1 week. Isn't it? Okay, my second last question. If any businessman, nuclear industry person sitting here, and you want a 50 crore or 100 crore deal and tell that your work is better, you can definitely go for this, it will work. Which ligand you will choose? Only one.
And butyl substituted, sir.
How many ligands you screened? Around 40, 50?
Yes, sir.
Huh? So that means remaining 49s are not good?
No, this is better.
Okay, why? Why it is better? N-butyl?
Substituted.
N-butyl, the triazolium, na?
Yes, sir.
Three benzene ring. Oh, this is the last chapter you are telling.
Yes, sir.
Why?
Sir, N-butyl, as you told, hydrophobic interaction, sir. That is the main reason. So
What about the price? What about the toxicity? What about is it available in India? What about the transportation, or from where to where? What could be the? Of course, you are not doing, but we should take care of everything.
Yes,
no?
sir.
Business means minimum investment, maximum profit. Okay, and no damage to environment. So, are you comfortable and are you confident that this work can be taken up by experimentalist or nuclear industry? And
Yes, sir. Sure, for sure.
Good. So, I am happy overall. All the best
Thank
and
you, sir.
congratulations.
Thank you, sir.
Have you seen the other? Huh? You can ask. I only have to ask. Okay. You have seen the external examiners questions or not yet?
Yes.
Have you made it slides?
No.
You could have made, then our job could have been easier. Okay, if you know, he had 5 questions. Okay, you remember any one?
Sir, he's asking about the salvation.
Yeah, explain about that first one.
So it's the fifth question. So basically, the limitation is that in computational chemistry, whenever we do gaseous phase, we can do it faster. Whereas in liquid phase, if we do, it takes more time. So in order to cut that, we only
Which
use.
is more close to the reality?
Sir, liquid only, sir.
That's it. Okay, next question, which is you remember. But did you mention this in the thesis?
Yes, sir.
Okay. Any other question? How do you envision the integration of emerging technology like artificial intelligence, machine, AI, ML, all are two letters. AI, ML, big data, and what potential advantage or breakthrough could use this DFT calculation? So he's telling AI is 2 letter, ML is 2 letter, DFT is 3 letter. You use 1 letter extra. What way it is advantageous?
Sir, so actually this can be further used by AI. So basically data can be generated. So the AI can utilize it and come up with more better options.
Your inputs can be useful there also?
No,
DFT?
outputs.
Outputs
Sir,
useful.
inputs.
In practical application of your research in nuclear waste management, how do you foresee the scalability of the? Of course, for you, scalability is in the computer only. You can add more molecule also, more ligands also, but in reality, in experimental, how it is will be in industrial setting is asking. And what challenges might arise in the transition from theoretical models to the real world application, and how could they be addressed? I think this I asked, but you
Yes,
can
sir.
answer again.
So again, same thing, sir. The gaseous phase only we are doing.
Is a question paper leaked? Huh? Already know the question. But this is a real world challenge, and
Yes.
people will ask you. You know your difficulties. People will know how to put you down.
True, sir.
You have to answer this. How you can compare experimental results? How you compare the calculation of gas phase to the reality of bulk phase?
Yes.
If it is matching results, and then I doubt your results. So you have to come up with the right answer. Because of the experimental limitation, funding limitation, manpower limitation, screening of so many ligands, instead of doing that, this will give you a better idea to go for which ligand.
Yes, sir.
I answered you, okay? Yeah. That's it. I think I more or less I asked all the questions from here. Yeah. I'm done from my side. No, any more questions from teachers?
Cheriyan, the presentation was good.
Thank you, sir.
I have few clarifications.
Yes, sir.
The cyclic substitution you are saying 5-membered aromatic ring optimizes binding.
Yes, sir.
So what about the 3-membered ring and the bigger sized rings? What is the effect of that one?
No, sir. 5-membered, so 3-membered ring we haven't checked. 5 and 6. So out of that, 5-membered aromatic ring is
So you
found.
checked only 2.
2.
5 and 6.
Yes, sir. And cyclic also, sir. Without the aromatic ring also we checked. So 5-membered aromatic ring is far better.
Is there any reason for choosing 5 and 6 only?
So experimental works have shown that 5 and 6 only. No one has experimentally 3, 2 is not possible. 3 and 4, it's not possible. We haven't seen, sir, any references for that.
3 is not possible.
No,
Cyclic properties are there.
no, 3 is there, sir. I'm not saying that 3 is not there. 3 is there, but for selective separations, we have not seen such substitutions.
Okay. Okay, so the alkyl substitution you are saying n-butyl groups, do you have the data about other substitutions?
Yes, sir. Yes, sir. And from the data, we observed that n-butyl is the best. From methyl, we started, sir.
Okay, is it there?
Yes, sir.
For different chain lengths, different
Yes, sir.
results.
So butyl is 4. So we have a separation factor of 9.79 into 10 raised to power 2.
Okay. Yeah, instead of we have 1, 2, 3, you have mentioned the ligands title, that will be better for us to understand. Yeah, thank you.
Hello, Cheriyan.
Hi, ma'am.
Congratulations.
Thank you, ma'am.
For a long time, you have been answering very in a cool way. I think within you would have been fearful, but you didn't show it out, and you have pleasantly answered.
Thank you, ma'am.
My simple question is: when you introduced this americium and europium, did you observe any ring strain there?
Yes, ma'am. We would observe that. We would observe that. So when I initially started, the calculation miserably failed because first of all, drawing the structure and then keeping it at the exact position, it's very difficult.
Okay, thank you.
Thank you.
Congratulations, Cheriyan.
Thank you, sir.
The presentation, but the questions by the examiner actually throw a lot of light and is able to understand. In the aim calculations, Q time calculations, you were talking about the electron density.
Yes, sir.
and all. The Laplacian of the electron density also is part of the results.
Yes, sir.
Does
Yes.
that throw any light, and does that give?
Yeah. So both.
Yeah, I did not see the
Yes, sir.
slide, so I don't know.
Yes, sir. Yes, sir. So basically, both the values are higher in case of Americium complexes than in European complexes. So that proves that the binding is greater in Americium complexes. Binding between the ligand,
You're talking about the Laplacian of
both
Okay,
electron density and Laplacian,
Laplacian.
ellipticity.
Okay, right. Thank you.
Good, Cheriyan.
Thank you, sir.
Why only American is most preferred over European? Can you tell me out of 5 chapter you got, what is the special feature which drives the higher binding affinity of Americium?
I didn't get you, sir.
Why Americium is superior than European? That's what your conclusion. No?
Yes, sir.
So what is the only one feature out of all the analysis you have done? The entire conclusion, if you say one word, what is the factor which affect the
HSAB, sir, hard soft acid base concept. So based on that only, we found out that so that is why we use end donor ligands. So as I mentioned earlier, americium is slightly softer than europium. So that's why we are using nitrogen donor ligands.
How did you calculate the separation factor?
So from del G, sir, we take a long natural of this del G value and we calculate, sir.
It is different from K or?
No, it's not K, sir. It is the log natural of the del G value.
Congratulations, Mr. Cheriyan.
Thank you, ma'am.
I am a person from a non-chemistry background.
Okay, ma'am.
Okay. So as a layman, I'm a layman. Okay. So in my understanding, could you please explain 2 important objectives and the relevant findings of your research, which I can understand?
So basically, ma'am, spent nuclear fuel. So once the nuclear reactor works, there is spent nuclear fuel. Okay. So in that many atoms are there. Okay, so we need to separate them so that their radiotoxicity can be reduced. So I am taking specifically americium and europium and trying to separate them using ligands. So finally, it's a very small thing. It's not that great. It's a very small thing. We just plan to separate americium from europium.
My boy, it is really great thing because Americium and European are in PPB level or PPM level.
Yes, sir.
And the industry has to spend a lot of money because they have to bury in the
Yes, sir. Yeah, ocean.
so many drums they have to fill. It is expensive. Not only expensive, it is a risky.
Yes, sir.
You have to calculate that even 100 years after that shark will not hit.
Hit.
How many drums you can put it? You are reducing the number of drums required.
Drums required.
Not you want to use americium and europium again, but the waste generation will be separated, so you can concentrate it and put it in small. It's a really needed work.
Yes, sir.
Okay? I'm sorry.
Thank you. God bless you.
Thank you, ma'am.
Sorry, madam, I told only 2 letters.
So I'm little curious to know, suppose say tomorrow somebody works as an extensive work of this in the perspective of AI, and you give a model. You say your model will be very good in the sense that you are very confident that your data is correct. And so what kind of model would you suggest, like for this kind of a data, this would be my classification or this would be my results. So how can that model be taken for an AI work later?
Okay, ma'am. So here we have done substitutions. So those substitutions can be further processed by the AI, and finally AI can screen many molecules based on the data that I have generated.
So you will give a result as yes or no. This
Yes,
is better
yeah,
and that
this
is better.
yes.
So
Based on few criteria.
thank
You want me to announce? Huh? You are standing, now you become outstanding, okay? So I have gone through the strongly, and as an external examiner, I am very happy with his thesis work, his presentation, and patiently answering all the questions and his understanding. So on behalf of entire committee, okay, it's my great pleasure to announce that Cheriyan Ebenezer should be given highly recommended for Ph.D. in chemistry from MCC and Madras. Congratulations. Okay. And after formally becoming doctor, anyway it may take few days, but now you are doctor, I would like to give him first gift, okay, and that too his own thesis signed by me with best wishes and 3.5 pages questions. So this is the best wishes from me. Congratulations. One more person to be congratulated is his guide. Please come for him. He is a first student. You come here. Many congratulations to you. All your chemistry colleague. One more photo and we'll close. We'll take it. Just want to say.
Just have a acknowledgement.
Just say thank you all.
Thank you all.
Yeah, don't be that one.
So I thank the Lord Almighty who has been with me throughout when I was born, throughout my career here in MCC, and after that I'm working in my school. He's been with me. Next, I would like to acknowledge Dr. Paul Wilson, Principal and Secretary, Madras Christian College, Dr. E. Ayyappan, head of our department. Whenever I go, he'll be there and helping us out. And then my guide should be given the first preference, but yeah, okay. So Dr. So Dr. R. Vijay Solomon, my research supervisor, and my doctoral committee members, Dr. E. Rajkumar and Dr. M. Jacob. Thank you, sir. Thank you very much, sir. And I would like to thank DST Serve. They provided me with the stipend. I thank them. Then some of my well-wishers like Dr. M. Alice Kibiot, Dr. D. Ruben Jonathan, Dr. N. Prabhu, Dr. S.T. Christopher Chandran, Dr. Tabitha Dure, Dr. B. Prince Solomon Devadas. These people were there throughout the PhD life I spent here. And some of my friends over here, research scholars, Mr. Priya Ranjan Dev, Mr. Rohit is here. Rohit, thank you very much, Rohit. Then my PG students, thank you for them. And some of my collaborators, I also wish to thank them. Thank you very much. Yeah, MCC, I thank MCC. Please join us for lunch.